Okay, so we continue with the 2017 JAMB question, and we start off with question number 33. We'll start off with question number 33 in the chemistry pass question. Let me quickly hide this question missing controls. Okay, so the question is the IUPAC nomenclature of the structure above is. The IUPAC nomenclature of the structure above is it 3-methyl but 3-in, 2-methyl but 1-in, 2-ethyl prop 1-in, 2-methyl but 2-in. So looking at that structure that we have there, what can you say the IUPAC name is? That is the IUPAC nomenclature. So let's carefully consider it, also remembering our rules for naming organic compounds. So first consider the functional group that is in that um, in that organic compound. Look out for the longest chain to determine, the name that you're going to give. That's the root name that you're going to give the compound. So you look at that carefully. Also look at the substituents and the position or the positioning of the substituents. So these are some of the things that you need to carefully consider in naming. And if you have considered all that, you should be able to arrive at the proper name for these compounds. So let me know what you feel the name is in the comment section while I review to you the name for these compounds. So the compound is actually called 2-methyl but 1-in. 2-methyl but 1-in. Why is it a but 1-in? Because the double bond is at the terminal carbon, which is the first carbon rather, the first carbon. So so that's why we have the but 1-in. So the double bond position is what gives us that 1-in that you're looking at. Then you have a substituent that is attached on the second carbon atom, and that is a methyl group, and that's why we have 2-methyl but 1-in. So just like what I explained before, identify the longest carbon chain with the double bond, and then thereafter number the chain from the end nearest to the double bond, So, and that was exactly what was done to arrive at these particular answer. Then identify and number the substituents, and the substituent in this case is methyl or methyl, and is on carbon 2. So from there you can actually assemble the name together. You know that is a 4-carbon chain, so it's a butane. Then you know that is a methyl group on carbon 2. And then the double bond starts at carbon 1. So with all that information, you can actually arrive at 2-methyl but 1-in, which is option B. Okay. Now let's look at question number 34 now. It said the reddish brown rust on iron roofing sheet consists of iron 3 plus water, Fe2.H2O, Fe2O3.XH2O, Fe3O4.2 H2O. The answer here is Fe2O3.XH2O. Now, the reddish-brown rust that forms on iron, such as roofing sheet, is primarily a hydrated form of iron 3 oxide. So that's why we chose Fe2O3.XH2O. Now, it results from the reaction of iron with oxygen and moisture, which is water in the atmosphere. So the general formula of rust is Fe2O3.XH2O, where Fe2O3 is iron 3 oxide, and then XH2O represent the variable number of water molecule attached. So this compound gives rust its characteristics reddish brown color. Okay. So the next one says that the densities of two gases X and Y are 0.5 gram per dm cube and 2.0 gram per dm cube respectively. What is the rate of diffusion of X relative to Y? The rate of diffusion of X relative to Y. Now, this can be calculated using the Gram's law. of diffusion. So if you calculate, what you'll be having will be 2.0. Then how did we arrive at this? By using rate of diffusion of X divided by rate of diffusion of Y equals to square root of density of Y divided by density of X. So if you plug in the values and you do it right, you will end up having 2.0 based on the values that we're provided with. Okay, so you end up having 2.0 as the rate of diffusion of X relative to Y. Okay, so we move along now. The carbon atoms on ethane are sp2 hybridized, sp3 hybridized, sp4 hybridized, and sp hybridized. So ethane is an alkane. The hybridization in alkane most of the time is sp3 hybridization. Alkanes have sp2, and then alkyne have sp hybridization. So the right answer here is sp3 hybridized, which is B. And just like what I just explained, it is just because ethane has the structure, and that's the structure there. And each carbon atom in ethane forms 4 single sigma bond, 3 with hydrogen atom and 1 with the other carbon atom. This type of bonding occurs when the carbon undergoes sp3 hybridization, meaning one s orbital mixes with 3 p orbitals to form 4 equivalent sp3 hybrid orbitals arranged in tetrahedral geometry. Okay, so that's that for that. So the next one says that according to Charles' law, the volume of a gas becomes 0 at A, minus 100 degrees Celsius, B, minus 273 degrees Celsius, C, minus 373 degrees Celsius, and D, 0 degrees Celsius. So when does the volume of gas become 0 according to Charles' law? The answer is, pardon me, please, is minus 273 degrees Celsius. That's when you have the volume of the gas becoming 0. So according to Charles' law, the volume of gas is directly proportional to its temperature, provided pressure is constant. As the temperature decreases, the volume of gas also decreases. Extrapolating this relationship shows that the volume of an ideal gas would become 0 at minus 273 degrees Celsius, which is defined as the absolute 0 or 0 Kelvin. This is a theoretical point where the gas particle would have no kinetic energy, not physically attainable, but fundamental in thermodynamics. Okay, so that's that for that. So let's move along now and look at the next one. It says an oxide XO2 has a vapor density of 32. What is the atomic mass of X? What is the atomic mass of X? The answer here is 32, option B, and this is how we come about it. Now, the first thing that we need to establish is the relationship between vapor density and molar mass. And we know from our lessons that vapor density VD equals to molar mass divided by 2. So molar mass is equals to 2 multiplied by vapor density. So if you are given a vapor density of 32 in the question, that means the molar mass will be 2 times 32, which will be 64 grams per mole. That's the molecular mass. Now, if the molar mass of the compound SO2 is atomic mass of X plus 2 times 16, 2 from oxygen times 16, that's 2 atoms of oxygen times the atomic mass of oxygen, which is 16. So when you do X plus 2 times 16 equals to 64, therefore X plus 2 plus 32 equals to 64, and X will be what? 64 minus 32. So the atomic mass of X will be 32 based on that calculation, okay? The gas that can be collected by downward displacement of air is A, chlorine, B, sulfur dioxide, C, carbon dioxide, D, ammonia. The answer is ammonia. And gases can be collected by downward displacement of air if they are less dense, that is, they are lighter than air. Now, when you look at the air, the density of air is about 1.29 gram per dm cube. Now, let's assess each of the gases that we are provided with as options. For chlorine, it is more dense than air because it is approximately 3.2 gram per dm cube, and it is collected by upward displacement of air. For sulfur 4 oxide, also denser than air, it is approximately 2.9 gram per dm cube. Carbon 4 oxide is slightly heavier than air. It is approximately 1.98 gram per dm cube. And then ammonia, much lighter than air, is approximately 0.77 gram per dm cube. Okay, so that's that. In the laboratory preparation of triazonitrate 5 acid and nitrogen 4 oxide, the nitrogen 4 oxide formed as a byproduct is removed by further heating, adding concentrated H2SO4, cooling the acid solution with cold water, bubbling air through the acid solution. So if you look at it closely, you see that the answer is bubbling air through the acid solution. And why did we choose that? In the laboratory preparation of triazonitrate 5 acid, HNO3, nitric acid is typically prepared by heating nitrate salts, e.g. KNO3, NaNO3, with concentrated sulfuric acid, And when you do that, you have that, especially when you use KNO3. However, in large scale or extended heating, nitrogen 4 oxide may be formed as a byproduct. This brown toxic gas dissolves slightly in HNO3 and contaminates it. So to remove NO2, air is what? Is bubbled through the acid. The oxygen in air oxidizing NO2, and then air carries it away, purifying the acid. Okay, so a particle that contains 9 protons, 10 neutrons, and 10 electrons is A, positive ion, B, neutral atom of a metal, neutral atom of a non-metal, negative ion. Okay, so looking at that, the answer is negative ion. Now, why did we choose that? The reason is because if you analyze the given particles, it has 9 protons, it has an atomic number of 9, and then it has atomic number of 9. So the element is basically fluorine. If you look at it based on the position on the periodic table. Now, neutron, it has 10 neutrons, and the mass number is 9 plus 10, which will be equals to 19. So the isotope is fluorine 19, and the number of electron is 10. So negative ion is what is formed. So when we look at the charge analysis, a neutral fluorine atom will have 9 electrons to balance its 9 protons. This has 1 extra electron, 10 electrons. That is a net minus 1 charge. So it is a fluoride ion, which is a negative ion. So that's how we arrive at the answer. Okay. So we move along that, talk about ethene is prepared industrially by reforming, polymerization, distillation, or cracking. So we talked about this in class, and the answer is cracking. So it is prepared industrially through cracking. And ethene, is a simple alkene and is one of the most important raw materials in the petrochemical industry. It's produced industrially through a process called cracking. And cracking is just the thermal decomposition of large hydrocarbon molecules into smaller, more useful ones. It is carried out at high temperature and sometimes pressure, often in the presence of of a catalyst. So during this process, alkanes from crude oil, e.g. decane, are broken down to produce alkanes like ethane and smaller, alkanes. So let's take note of that. The next one is calculate the amount in moles of a gas which occupies 10.05 dm cube at 6 atmosphere and 30 degrees Celsius. We are giving our R, which is a constant at 0.082 atmosphere dm per Kelvin per mole. So we have the options there. So let's work it out and see what we can get as our answer. So the answer to this one is 2.536, and the formula that we make use of is the ideal gas equation, which says PV equals to nRT. Our P in this instance is the pressure, which is about 6 atmosphere. Our volume is 10.5 dm cube. Our temperature is 30 degrees Celsius. And then R, which is the constant, is 0.08 82 atmosphere. So given those parameters, we can actually solve for N. That's the number of moles by making N the subject of the formula. So that will give us PV over RT. So when we substitute the values, what we'll end up having as N will be 2.536, which is option A. If 100 cm cube of oxygen passed through a porous plug in 50 seconds, the time taken for the same volume of hydrogen to pass through the same porous plug is it 10 seconds, 12.5 seconds, 17.7 seconds, 32.0 seconds? The answer is 12.5 seconds. How did we arrive at that? Rate of diffusion of hydrogen divided by rate of diffusion of oxygen, which equals to square root of the molecular mass of oxygen over molecular mass of hydrogen. So when you do that, you plug in the value, you end up having the time that it will take it to for the same volume of hydrogen to pass through to be 1/4 times 50 seconds, which was the initial one. So 1/4 times 50, which will be us now 12.5 seconds. Okay. Due to high reactivity of sodium, it is usually stored under water, mercury, paraffin, phenol. It's reactive, so it is stored in a way that it will not reacts, with other constants that it's not supposed to. So the storage most of the time is done under paraffin. So the answer is C, and sodium is highly reactive alkali metal, especially with water. It reacts violently, producing nitrogen gas and sodium hydroxide, often with flames. And then air with oxygen and moisture reacts quickly to form sodium oxide or hydroxide. So to prevent such reactions, sodium is stored in a non-reactive, airtight medium that prevent contact with air and moisture. Okay, so let's take note of that. The next one says that the thawing of kettle is caused by the presence in water of calcium hydrogen triazocarbonate 4, calcium triazocarbonate 4, calcium tetra oxo 6, and calcium hydroxide. So looking at the options carefully, the right answer is actually B, calcium triazocarbonate 4. Thawing of kettles refers to the formation of a hard white crust limescale on the inner surfaces of kettles, boilers, and eating elements. This is due to the precipitation of calcium salt when hard water is heated. So this is how it happens. Temporary hard water contains calcium hydrogen carbonate, which is soluble. Upon heating, it decomposes, and when it decomposes, it composes into calcium carbonate, water, and CO2. So the insoluble calcium triazocarbonate 4 precipitates forming thawing or scales in the kettle. Okay, water for town supply is chlorinated to make it free from A, bad color, B, bacteria, C, temporary hardness, and then permanent hardness, which is our D. So why do we add chlorine? Chlorine basically is added in order to combat, germs and bacteria. So the answer to this one is B, bacteria. So chlorine is a key step in the treatment of water for town or municipal supply. It involves adding a small amount of chlorine or a chlorine compound like sodium hydrochloride to water to disinfect it. So the purpose of chlorination includes to kill bacteria, virus, and other pathogens, to prevent waterborne diseases such as cholera, typhoid, and dysentery, and also to help maintain water safety during distribution. Okay. So the next one says that looking at that equation, in the equation above, X is what now? Is it NO2, Na3, N2O, or NO2? What is X? If you look at the equation closely, you discover that our X should be ammonia. Ammonia should be our X in that equation. And the explanation is that ammonium chloride reacts with calcium hydroxide, and then ammonia gas is liberated along with calcium, chloride and water. So that's that for that. So X is actually ammonia. Okay. So this is the balance reaction with X. You can see that X in this regard is equals to 2 moles of ammonia. Okay. So X gram plus 3Y gram will give us 2Z gram. Hydrogen is positive. If the reaction above takes place at room temperature, the G will be negative, 0, positive, indeterminate. It will be positive. The G will be positive. And the reason is because the question is based on Gibbs free energy, delta G, and how it is influenced by enthalpy change, delta H, and entropy change. So now given this particular, formula, sorry, given this particular equation, you have your delta H to be positive. That is an endothermic reaction. The reaction is taking place at room temperature, and we are to determine the sign of delta G. For us to be able to do that, we use the Gibbs free energy equation, which is equals to delta G equals to delta H minus T delta S rather. So analyze the entropy change and reactants, 1 mole of X plus 3 moles of Y, which equals to what? 4 moles on the reactant side. And the product, you have 2 moles of Z, which is like equal to 2 moles of the gas. So decrease in the number of gas multiplies gas molecule is synonymous with delta S, which is negative. Okay, it's synonymous with delta S that is negative. And therefore, plug into the Gibbs free equation. Delta H, when equals to is positive, delta X is negative, T is always positive in Kelvin. Then delta G plus minus T minus equals to plus plus plus. That's positive. So it will be positive. So for this one, the G will be positive, okay? Thank you very much for joining me in this past question. So providing past solution to the past question. I hope you got something profound in the solutions that was provided and the explanation given. So I'll see you in the next video as we continue with another year of the chemistry JAMB question. Thank you for now. Bye bye.